Okay, good afternoon, everybody. I see people are still joining, but we are actually at the start time, so we'll begin. I'd like to introduce our speaker, Shannon Gallagher from HSM Development, who is working at an unsocial hour to give us this presentation. It's a topic which I think probably exercises every installation that runs HSM seriously, and it has done for as long as I can remember. Well, perhaps not the CPU part, but certainly elapsed times. So I'm sure there'll be a lot in this presentation that will be of value to anybody who's involved with running a large HSM installation. A little bit of admin. If you haven't already done so, then please open your chat window. And if you have any questions that you would like to answer, please put them in the chat and we'll cover them at the end of the session rather than during the session. At the end of the session, we'll do a wrap up, answer the questions, and I'll then unmute or allow you to unmute yourself so that we can have follow-up questions or follow-up discussions. So if you'd like to do that, that's proven to be a fairly good way of running the Zoom conferences. And with that, I'd like to hand you over to Shannon to tell us about how to minimize HSM CPU time and elapsed times. Thanks very much, Shannon.
Yep, thank you, Nigel. I am a senior developer on HSM Squad, and I am excited to have the opportunity to share with you today about this important topic. There really is a lot of valuable information to cover in this session, so I'm just going to dive in and get started. We are here to explore methods for minimizing HSM CPU utilization and improving HSM's performance. And as Nigel indicated, this is an important topic because HSM is typically one of the largest MIPS consumers in an enterprise. So in large environments, HSM moves close to 200 terabytes of data a day. And it's this data movement that causes HSM's high MIPS consumption. Also, depending on when your HSM activity occurs, it can contribute to your peak rolling 4-hour average, which could obviously cost you more money than necessary. But fortunately for HSM users, HSM strategic direction aligns with minimizing CPU utilization and elapsed times. And as you can see here on the slide, HSM's strategy is to get out of the business of physical data movement by offloading the movement to storage controllers, and to be a thin, automated, policy-based data manager that provides cyber resiliency and lifecycle management. So I invite you to consider what you're doing or what you're planning to do to keep up with HSM's evolution, because keeping pace with this evolution is going to result in significant benefit and cost savings to your business. So before we take a look at the agenda, excuse me, I want to point out that Frank Kine and Glenn Wilcock wrote a Watson and Walker article dedicated to this topic. And if you'd like to dig deeper into the information covered in this presentation, I recommend you check this out. It's a great article. So here is our agenda for the session. First, I will talk about how to capture and process data to gain insight into your HSM environment and determine areas where you can benefit from change. I'll talk about functions that everyone can use to quickly and easily improve HSM CPU or HSM performance and reduce CPU. And I'll cover functions that require more significant change. We want you to know we really do understand that making changes to your HSM environment is challenging and it involves risk. So we're not surprised if your response to making change is something like this here on the slide: change is good, but you go first. But we really do want you to consider these more significant changes and newer technologies, just because, as I already mentioned, it really can make a significant difference in cost savings and performance for you. So as I mentioned, HSM collects data that you can use to identify areas where you can benefit from change. HSM captures important information about its processing in SMF records, such as FSRs, DSRs, and VSRs. Now, the FSRs are function statistics records, and they provide information about each function that HSM executes. And there is one FSR for each request processed by HSM. Now, these FSRs, they're especially helpful for gaining information needed to make improvements to your HSM processing, because they contain specific details that you'll need to do this. FSRs are written to the SMF data sets and the HSM log. And then daily statistics records and volume statistics records, they provide daily stats on HSM operations and volume activity. HSM writes 1 DSR per day and 1 VSR per volume under HSM control per day. And these records contain information that are accumulated from the FSRs. They're written to the MCDS and also the SMF data sets. So by default, HSM does not write these records to SMF. So you'll want to enable HSM to write these records, and you do that by specifying setsys SMF along with a number that HSM should use for the SMF record type. So it's recommended that you use type 240. HSM will use this record type that you specify on that setsys SMF command for the FSRs and DSRs, and then for the FSRs, HSM will increment that specified record type by 1. So if you specify the recommended 240, your FSR records would have type 241. The formats for these records, they're not in the SMF manual. You'll find them in the HSM data areas manual. And then additionally, you can use dcollect, which is the Access Method Services data collection application. You can use that to extract helpful information about HSM's processing from HSM's control data sets. So once you've enabled HSM to write SMF records, you can use various applications to generate useful reports from that data contained in those records. So one of these applications is IBM's RMM report generator, and it's an easy to use ISPF application, and it's available to all HSM users because it's included with ZOS. The HSM Storage Administration and RMM reporting publications contain information on RMM report generation, and that Watson and Walker article I mentioned, it also has some helpful summary information. So the RMM report generator, it cannot process the FSR records exactly as they are written. So it converts FSR records to FSR2 records. And on the top and the right of the slide, you see an excerpt from the HSM data areas publication for the FSR2 record. And it lists, you see here on the right, all of the functions that HSM writes FSR records for. You can see there are a lot of them. So I mentioned on that last slide that FSR records, they're especially useful because they contain detailed information, and some of the most helpful fields that you need to collect information to determine where you need to reduce some CPU are in these fields listed here in the box on the left. So FSR2 CPU, it provides obviously the CPU time for the request, and the time is captured in hundredths of a second. And it's important to note that the granularity of a hundredth of a second, that's actually too large for requests for smaller data sets. So in these cases, you may see FSR2 CPU of 0. So obviously you want to be careful when you use this field for analyzing trends for large data set, or you want to use it for large data sets. You want to be careful for small data sets how you're using that information. It's also important to note that the CPU times will vary. There are many reasons for which this can occur they're outside of HSM's control. An example of this is NQ processing. Since in some instances, a request can be delayed while HSM is waiting for dataset serialization. So that's obviously going to impact the CPU time. The return code and reason code and FSR2RC and FSR2RES, those can be used to identify trends and errors. And then the remaining fields at the bottom provide information on the number of bytes and tracks read and written. So this slide shows some sample reports that are already available in the RMM reporting tool. And here you can see there are reports to capture statistics on various HSM functions and also things like DASD and tape capacity. So one example of a very practical use of an HSM report is eliminating migrate and recall thrashing. This HSM thrashing report, it shows data sets that are recalled soon after being migrated, and by default, the port will include data sets with a migration age of 0 when the data set was recalled. So that means that the data set was recalled on the same day it was migrated, and you obviously do not want that happening. So you can quickly identify the large data sets at the top of the report. And then to prevent thrashing, you would update the management class listed in the report, and you would do that by increasing the primary days unreferenced setting in the management class. So in this case, for this example we have on the slide, management class M class 1 would be updated, and that primary days unreferenced would be changed. And if that new setting doesn't apply to all of the data sets assigned in the management class, you could obviously assign a subset of data sets to a different and more appropriate management class to handle that. Reports can also help you to eliminate daily exception handling. You can generate a report for all functions that have a non-zero return code and reason code. And then you can use that report to identify error trends and appropriately address them. You can also generate a report for data sets that are repeatedly skipped during HSM primary space management. And by default, FSR records are not written when data sets fail space management eligibility checks. So an example of this is when a data set is expiration eligible, but no backup of the data set exists. And in this case, an ARC 734I message would be issued. So you can specify that FSR records should be created for these 734I errors during primary space management, and you would issue the patch on this slide to do that. And this will allow you to generate a report for these cases and then take action as you need to. So here we have a couple of simple yet beneficial hints related to data set allocation. It's common practice to start a job with an IEF-BR14 step that deletes an old data set. However, when the data set is migrated, HSM will first recall the data set and then allocation will delete it. So this obviously is resulting in unnecessary data movement that you are paying for. So you can update the alloc member of ParmLib to specify no recall for IEF-BR14 del MIG-DS. And this will ensure that the data set is simply deleted without HSM first recalling it. And then when you have a batch job that needs multiple data sets that have been migrated, the default behavior is for HSM to recall them one at a time as the job encounters them. And so you can change this to speed up your batch job by directing allocation to identify all the migrated data sets in this step and then recall all of them in parallel. And you do this by updating the ARC alloc XX member of ParmLib to specify batch recall MIG-DS parallel. So since these are easy improvements, your homework is to issue the display alloc options. Oops, sorry about that. Display alloc options command that you see here on the screen. And this you can determine then if you need to update these settings here on this slide. So if you have a rolling 4-hour average pricing model and HSM is a significant contributor to your peak rolling 4-hour average, you'll want to look into decreasing the maximum number of concurrent HSM tasks. Obviously, the more tasks that are running simultaneously, the higher your peak rolling 4-hour average is going to be. So decreasing the number of concurrent tasks, that obviously involves extending HSM's auto processing windows. And this just really allows more time for HSM to complete all of that workload within the available time frame. So this chart shows an example of a client that implemented this type of change. And you can see here, the client had a 3-hour auto processing window with a 1200 MIPS peak. And by increasing their auto processing window by 2 hours, the MIPS peak was essentially cut in half. So that's a pretty significant difference. We encourage HSM clients to enable fast subsequent migration. FSM eliminates unnecessary data movement when remigrating a data set to tape that was not updated since the recall. So here on the left, you see the default behavior without FSM enabled. So we have an inactive data set that's migrated from primary storage to tape. And then the data set is recalled so that it can be read, but it's not updated. So now you can see the tape that it resided on has some invalid data on it. And then later, the data set's eligible to migrate again. It migrates to a new location. And since the original tape has invalid data on it, it can be recycled to a new tape, and then the original tape is scratched. So this is obviously a lot of processing. But here on the right, you can see what happens when FSM is enabled. And as before, a data set's migrated, and then it's recalled to be read. However, this time you can see HSM keeps a pointer to the location on the tape. So when it's available for migration again, and if it hasn't been updated since the recall, HSM can simply just reconnect to the original tape and update the catalog without performing any data movement. So clearly there are multiple advantages of fast subsequent migration. There's no actual data movement for reconnection. The recycle workload's reduced and the reconnection is done automatically. So FSM is controlled with the setsys tape migration reconnect command, and the default is none. So the feature is disabled by default. So to enable this, you want to specify all to reconnect when the data is eligible for either migration to migrate to ML1 or ML2, or you can specify ML2 direct to only reconnect when the data is eligible for migration to ML2. HSM does not keep those migration records around indefinitely. So you can use the setsys migration cleanup days to increase the number of days that HSM will keep the records if you think you may need them around for a bit longer than normal. Otherwise, there's a predicted recall date that HSM uses to determine how long to keep all of those migration records around. So if your HSM CPU report shows a spike at the top of each hour, interval migration is the cause. And this slide shows how interval migration works. Throughout the hour, primary space management, oops, sorry about that. I went backwards instead of forwards. Primary space management volumes, they're exceeding their threshold. And you can see here some of them to a significant extent. Those darker volumes are showing that they're getting close to the maximum amount of space being used. So then at the top of the hour, HSM initiates an SMS scan and a space check on all of the volumes in the SMS plex so that it can free space on the volumes, and this hourly spike can be eliminated using on-demand migration. So here we can see when on-demand migration is enabled, as soon as the volume reaches its high threshold, HSM is going to immediately process that volume. So the volumes always have the sufficient free space that they need, and then this hourly spike is eliminated. You'll also want to ensure you've applied OA 59038. This APAR fixes a CPU issue that occurred during startup. And then you can enable on-demand migration with this command up here at the top of the slide. It sets this on-demand migration, yes. So throughout production, interval and on-demand migration, they ensure that a minimum level of free space is maintained. I'm sorry, I just got distracted by something. So what you can do is with ZOS 2.4, you can quiesce event-driven migration. And this is helpful because sometimes on-demand migration or these other interval migrations, they can contribute to your peak rolling 4-hour average, and you don't want that happening. So what you can do is just enable this event-driven migration quiesce, and that will ensure during heavy times of CPU consumption, you can specify up to 2 windows where HSM won't process event-driven migration. And then when event-driven migration is quiesced, the command migration can still be processed. And then you can also hold event-driven migration if you want to manually prevent event-driven migration from running indefinitely. So that's just really nice. You can kind of control these things that would normally automatically kick off and contribute to your peak rolling 4-hour average. So if you'd like to improve migration elapsed time, you can take advantage of migration subtasking. And for small data sets, pre and post processing accounts for up to 2/3 of the overall processing time. So that's obviously a lot. So you can see depicted here on this slide, when a data set is migrated, HSM first performs these pre-processing activities, then HSM moves the data, and then there are post-processing activities that HSM performs. And HSM will do this for each data set serially. So then you can see down here at the bottom of the slide, just this fraction of the overall processing time actually accounts for data movement shown in yellow. So this elapsed time can be significantly improved by enabling migration subtasking. And with this feature, multiple data sets are processed concurrently, and the pre and post processing overlaps with the data movement, as you're seeing here on this picture. So then you can see down here at the bottom, with migration subtasking enabled, the majority of the overall processing time is primarily that data movement, instead of what we saw on the last slide with all of that overhead of pre and post processing. And then on this slide, we see expected improvement with migration subtasking. The blue bars represent results when migration subtasking is enabled, and the orange is when it's disabled. And in a controlled environment with a tasking level of 8, you can see we experienced 100% throughput for small data sets with very minimal MIPS increase. So that's substantial. And migration subtasking, it can be enabled for primary space management, on-demand migration, and interval migration by specifying set-sys migration subtask yes. And the default number of subtasks is 5. This is a patchable value. And 5 is the default because our testing revealed that 5 subtasks was optimal, but the maximum number of tasking is 105 tasks. And as I mentioned on the last slide, although this enhancement, it does significantly reduce elapsed time, it does slightly increase CPU. There is a new DSS APAR OA 58019 that will reduce CPU in DSS and HSM when processing extended format data sets that are not striped. So we found that clients that were converting from basic sequential to extended format data sets for encryption purposes, they noticed a CPU increase in DSS and HSM, and this APAR addresses that. So you'll want to ensure you have that applied. And then since data movement is the biggest cost of data management, you obviously want to move less data whenever possible. So in the following slides, we'll talk about various approaches to moving less data. This slide lists a few of those approaches. First, you don't want to move small data sets. The good news is that the SMS management class now enables size-based space management to allow for this. Second, you want to use ZEDC to compress the data so that you move less of it. And third, you want to use disk tiering and class transitions if possible. So if you aren't using ZEDC, you should definitely consider it. ZEDC will improve HSM throughput and reduce CPU more than any other change. An HSM client actually made the comment that with ZEDC, HSM recalls were running too fast. So when using ZEDC, DSS will first compress the data before passing it to HSM. And so HSM in this case is processing significantly fewer blocks because of this. We've had many HSM clients have a ratio as high as 8:1 for HSM ML1 and backup data sets with ZEDC. So this next slide shows the comparison of traditional HSM compression and ZEDC compression when migrating to ML1 DASD. On the left, you see that for HSM compaction, there's the CPU in blue, elapsed time in red, and the space utilized in yellow. And on the right, you see these values when using ZEDC compression instead of HSM compression. So with ZEDC, up to 80% MIPS reduction was experienced, and up to 50% less space was used. And that's obviously a huge difference. And with the Z15, the compression, this is even better. So here we see why using ZEDC makes such a difference. Over here on the left, you see when migrating or backing up data to ML1 using standard processing, DSS reads the data and passes it to HSM, and then HSM compresses the data, blocks it in 2K blocks, and writes it to ML1. And as you can see, the amount of data going through the host is going to result in significant CPU and elapsed time. And then you can contrast that with here on the right, when DSS invokes ZEDC for compression, there's significantly less data for HSM to block and write, and that's reducing the CPU and elapsed time. Also, since ZEDC compresses better than HSM, less storage is needed, and ZEDC is also beneficial for secondary space management processing since there are fewer blocks to write to ML2. APAR OA 57834 has added compression information to the FSR so that you can get some stats on all of this. And here we see the same scenario as the previous slide, but in this case, the source data is already compressed. Without ZEDC, HSM performs compression, even if it was already compressed with HSM compression. And then with ZEDC and with APAR OA 55320, DSS, it recognizes when the source is already compressed and it passes that data directly to HSM without attempting to further compress it. When migrating and backing data up to tape, you see here on the left, DSS reads in the data, HSM blocks all of that data into 16K blocks before writing to the TS7700. Yet with ZEDC, HSM again, it's blocking and writing significantly less data, and that's overall less CPU and decreased elapsed time. And then finally, with migration and backup to tape, when the source is already compressed, standard processing doesn't have any additional overhead added. And with ZEDC, DSS again is recognizing that when the source is already ZEDC compressed, and it's passing that directly to HSM to write. So now let's transition into the topic of the evolution of data movement. And I mentioned early in the presentation that HSM's strategy is to get out of the business of physical data movement and rely on the storage controllers to move the data. And this serverless type of data movement, it began decades ago when flash copy was introduced. And as you know, with flash copy, HSM can direct the storage controller to move data from one logical volume to another using track-based movement. Disk tiering also performs another form of serverless data movement. With IBM Easy Tiers, a DSA-K can be configured with a mix of drives. And you can see those listed on the bottom left: performance flash, capacity flash, and maybe even spinning disk. And the disk controller moves that data throughout the hierarchy of devices based off the data's temperature or how often it's accessed. And tape tiering also provides that serverless heat map based data movement. But unfortunately, the hardware does not provide the ability to move data in between these disk and tape tiers, which is why you see this brick wall here. So when thinking about your tiered environment, we want you to really question your use of HSM's ML1 and ML2 tiers and how your environment is serving your business, especially as technologies are changing. So ML1 obviously allows you to get your migrated data faster. However, as you know, having a mixed ML1 and ML2 environment, it incurs additional costs with this double data movement, and there's MIPS for software compression to ML1. So here are some options that clients are considering. Some small clients are eliminating ML1 and ML2 altogether, and this is because of the decreasing cost of storage. Smaller shops can then keep all of their data online and just take advantage of disk tiering to minimize their cost. You can consider an ML1 only environment. It has the benefits of a homogeneous storage environment, parallel data access, and no need for recycle processing. However, you need to consider the UCB limit as these ML1 volumes consume UCBs. Going to an ML2 only environment has several benefits as well. The tape controller can tier data between the disparate storage. The large caches eliminate the overhead of the tape mount, and ZEDC has enabled all cache hits for recalls. But the negative here is the serial data access, which obviously increases recall time. So again, if you have a mixed ML1 and ML2 environment, you may want to consider whether using a different option might serve your business better. There are other tiers to consider besides the traditional ML1 and ML2 tiers. The DS8K, as I mentioned, provides storage tiering. And with storage tiering, the storage controller's heat-based extent data movement allows you to keep inactive data online on the lowest cost media. So this is ideal for data that's not eligible for migration or that has a short life, and also small data. This diagram on the left shows how over time an easy tier device balances data across ranks to maximize throughput and efficiency. And the diagram on the right shows that over time, the controller learns and balances the data, and your throughput is improved. So clearly, storage tiering provides an efficient and cost-effective means of storing your data. So by combining disk tiering with HSM's class transition support, you can achieve serverless data movement between online tiers. So the key here is that class transitions provides a way to guarantee data of lower business value remains on the lowest cost online tiers. And with class transitions, flash copy can be used to move the data in a serverless way. And data is moved down to another online tier as it changes from being active to more historical in nature. You can leave the data online longer in its original format until it's ready for archival to ML2. And data can be moved laterally to other devices as needed. And this is commonly done for situations such as, if you're increasing the size of your volumes or you have a data refresh or device refresh. So this slide depicts how storage tiering and class transition works. And on the left side of the chart, you see the temperature scale. As I mentioned earlier, it's a measure of how often the data is accessed. The hot data is being accessed frequently and frigid is not accessed at all. And here on the slide, we have an example environment with a primary storage hierarchy where an easy tier device is the primary tier, tier 0, and data is allocated to that easy tier device, and the storage controller for the device just transparently moves data up and down within that smart tier based on the temperature of the data. And then over time, as the data is accessed less frequently, but it's still accessed enough for it to warrant it staying online, DFSMS can transition the data to media defined in a lower cost tier in the primary storage hierarchy using flash copy. So this obviously is freeing up valuable space on that easy tier device so that new data can be allocated to it, but it's guaranteeing that the data is remaining on that lowest cost online storage. And then once the data is cold, HSM can migrate it to the migration hierarchy for archival purposes. So data can be moved to various levels in that migration hierarchy as needed as well. And this type of tiering that's shown on this slide, it's perfect for data that has decreasing business value. And there's also a couple of important goals here that we want to keep in mind. The first goal is we want to minimize the cost of storing data that's never migrated. And then second, we want to minimize migration thrashing by maintaining data in the online hierarchy for a longer period of time. So here we see how HSM manages data movement. Oh, whoops, sorry about that. So here we see there's 5 physical tiers in the storage hierarchy. And in the primary storage hierarchy, we have disk tiers of performance flash, capacity flash, tape cache, and then in the migration hierarchy, there's tape cache, physical tape, and a tape cloud tier. So what's important to know is that the control unit tiering, it's transparent to HSM. So you can consider these as black boxes to HSM because HSM is only aware of these 3 logical tiers, the smart tier 0, tier 1, and ML2. So you may be wondering, how does all of this reduce CPU? And we're going to cover that here on these next few slides. On this chart, we see how HSM manages data movement without class transitions. So this chart is showing the activity level of a data set as it ages, and you can see for a period of time after the data set was created, that data set's temperature is hot because it's being frequently accessed. But then as it ages, the frequency is diminishing. The frequency of access is diminishing. And then the data set during that time may go through multiple migration recall cycles before it's migrated for a final time. So obviously, all of this movement is incurring cost. And so here we see the difference when HSM is managing that data set with class transitions. So you can see there's a single class transition that replaced those multiple migration recall cycles, and that's reducing CPU. And then that data set's not migrated until it's very cold and it's no longer really being accessed at all. So here we see another way to depict how class transitions minimizes CPU utilization. And up here at the top, we have an example of HSM processing without class transitions. First, when the data set's eligible for migration, HSM migrates it to ML1 with compaction. And then later, it's migrated to ML2. And then the data set needs to be recalled back to primary to be read or written to. And then later, it's eligible to migrate again to ML1 with compaction, and then finally migrated to ML2. And then here at the bottom, you see with class transitions, if flash copy is used as the copy technique for the class transition, it's only a minimal amount of HSM MIPS that are used to process that movement. And then there's a final migration to ML2. So you can see here that the total processing, HSM processing, is drastically reduced when you're using class transition. So you define tiers to DFSMS within storage groups, and that's essentially what you're normally doing. So it's nothing new. This slide shows a sample environment in which volumes are defined in an extent pool of performance and capacity flash devices. Those are defined within SG tier 0. And then volumes defined in an extent pool of only capacity flash devices. Those are defined within storage group SG tier 1. Then ACS routines are also configured, and they're set up so that data sets are initially allocated to SG tier 0. And then the ACS routines also will be configured so that when a data set is eligible for automatic transition, HSM will transition that data set to SG tier 1. And this will ensure that that data that goes to SG tier 1, it will reside only on capacity flash and won't be moved back to performance flash. The SMS management class provides 3 class transition policies. There's the class transition criteria that indicates if and when a data set should be transitioned. There's a serialization error exit that indicates what should happen if a data set can't be serialized. And then there's the transition copy technique, which indicates how the data set should be moved. So we'll cover each of these a little bit more in depth on the following slides. Within the management class, you set the class transition criteria to indicate when the data set defined to the management class should be transitioned. And the default is to not perform class transitions. So if you want to set up class transitions, you'll need to specify just one of these 3 other criteria. If you specify time since creation, the data set will be eligible for a transition on or after that time that you specify. For time since last use, the data set would be eligible for transition on or after that specified time. And then if you want to specify periodic, the data set will be eligible for transition on a specific date. So here we see the management class define panel where you set up the class transition criteria, and you can see the time since creation and time since last use can be specified in years, months, or days, and periodic can be specified on a monthly, quarterly, or yearly basis. The second class transition policy is related to dataset serialization errors. And as I mentioned, the time since creation and the periodic transition criteria, those indicate that transitions should occur on a specific day. So if the data set happens to be in use at that time and it can't be exclusively serialized for the transition, this serialization error exit setting, it indicates how this situation should be handled. So an example is database data. It's expected that in this case, for database data, the data set is always open. So special processing is going to need to be done to transition that data set that's open. So the default setting is to skip the data set if it cannot be serialized and not issue an error message. So to issue a message, you can issue the patch here on the slide. Also, an FSR record will be cut for this condition to enable reporting for this scenario. So the management class provides multiple serialization error settings. If a serialization error occurs, HSM, it's going to use these settings to determine what it should do next. So if none is specified, that's the default, the data set is not going to be transitioned. But if one of these other settings is specified, HSM is going to use this setting to notify DSS of which application needs to be invoked for this case. So HSM will invoke the specified application or exit, and then the appropriate action can be taken so that the data set can be serialized. And once it's serialized, DSS can then perform the transition, and then DSS will re-invoke the application or exit to restore the data set back to its original open state. The transition copy technique, it indicates how the data set should be moved, and you can specify standard IO, fast replication, or preserve mirror preferences and requirements for that. This slide shows that storage groups and ACS routines can be configured in any combination to transition data from one set of devices to another. So you can transition data sets within a storage group to other volumes in the same storage group, or from one storage group to another. You can also transition from one to multiple storage groups or multiple storage groups to a single storage group. And this type of movement is especially helpful when you need to make an SMS configuration change, or when you're increasing the size of volumes or performing a device refresh. So now we come to cloud storage. This is our final topic in our discussion on reducing HSM CPU utilization. And cloud storage is exciting because it provides automated policy-based serverless movement between online and offline storage. So you see, once we had that large brick wall in between the online and offline storage, you can now see that with cloud, that barrier between online and offline storage is broken. With this support, the DS8K interfaces directly with cloud object storage and no additional appliances are required. This is done over existing Ethernet ports, and the support can be used with both on and off-prem clouds. And since fourth quarter of 2019, you can use the TS7700 as a cloud. In this case, DFSMS communicates with the DS8K through the cloud interface, just as it does for other types of cloud storage. And then the DS8K ensures that the data is stored directly as objects on the TS7700. With HSM, you can set up automatic policy-based serverless data movement throughout your hierarchy, including cloud now. And so just to simply state this, cloud storage is a new tier that's been added to the storage hierarchy. So you may be wondering, why should you put in effort to set up your environment to send data to the cloud? And one of the primary reasons is the entire focus of this session. It's to cut down on HSM CPU. The simple API used with cloud processing is what enables this. And here at the top, you can see there are many APIs involved in writing data to virtual or physical tape. There's allocation, mount, rewind, write, read, sync, and the volume processing. And the red box on the right, it shows a summary version of the algorithm when directing data to tape. So you need to, first we would need to select a tape, allocate a drive, invoke DSS, DSS reads that data and passes it to HSM. HSM's reblocking the data, writing it over the channel. You sync the data on tape, handle end of volume spanning, file block IDs, all of that processing. And in addition to that, as the data expires and it's deleted over time, the tape data needs to be recycled to remove empty gaps on the tape. And it's causing data to be written yet again. So if you contrast that with what is required to archive data to the cloud, the API is simple. There's put, get, and delete requests. And the algorithm is if cloud, invoke DS8K to put the tracks in the cloud. So that's obviously pretty simple. It eliminates a lot of CPU, which is why leveraging the cloud for your data archival purposes saves you money. So to summarize and reiterate, utilizing cloud storage is a great way to eliminate constraints. It allows you to reduce CPU, as I just talked about. You can co-locate like data. It streamlines HSM inventory because the offline control data set is no longer needed. It eliminates 16K block size, dual data movement, recycle, and serial access to tape. So if you're wondering just how much CPU you can reduce by leveraging cloud storage, the next few slides are for you. This slide provides a relative comparison of the amount of CPU saved based off data set size. So up here on this top left, you see the blue arrow that shows activities that consume CPU during pre-processing when migrating a data set. The yellow is the processing during data movement, and red is post-processing activities. So on this bottom left here, you can see that for small data sets on the very left, the amount of CPU consumed for pre-processing, data transfer, and post-processing is about the same. But then as the size of the data set increases, and you look to the right, the amount of CPU consumed for data movement is increasing proportionally. So here on the right, you see that with TCT, large data sets consume the same amount of CPU as the smaller data sets. This slide shows results of some internal IBM testing. Migrating a 5 GB data set to ML2 took about 7.5 CPU seconds, where migrating the same data set to cloud took only 0.05 of a second. And this scatter plot of data sets that were migrated during primary space management gives some helpful information. The plot shows the data set size versus the CPU time. And it was generated from actual client data using their FSR records. So the FSRs that did not move data, those were removed from the scatter plot. And you can see here that the data is very linear in nature. As the size of the data set grows, the CPU seconds increase at a fairly constant rate. So from this data, you can conclude that migrating large data sets to cloud will result in significant CPU savings. So here we can see the type of CPU savings you can expect. This shows a comparison of the client's actual CPU for daily primary space management migration with the estimated CPU when migrating to cloud. So consistent with the internal testing and the client's data, the estimate of 0.06 data per second was used for migration to cloud here. And the dark blue bars, they show the actual CPU when migrating to ML2. The orange bars show the number of tracks migrated, and the light blue is showing the anticipated CPU when migrating to cloud. So in this customer environment, more data is migrated on some days than others. So the more data that's moved on a particular day, you can see more CPU savings are experienced. So here you can see the range from 46% to 78%. Savings. So it's important to remember that the reduction that you're going to see, it depends on the size of the data being moved. So clients who are moving smaller data sets, they're going to see more modest reductions. So the initial use case for TCT is to target HSM automatic migration to the cloud. And you do this by setting cloud as the migration tier in the management class. And it's important to know that migrate recall through Ethernet is currently slower than FICON to virtual tape. So when you set up the management class, you want to target data sets for which lower recall is acceptable. And another initial TCT use case is to store DB2 image copies in the cloud without sending the data through the host. And this slide depicts how to do that. First, you'd create point-in-time DB2 image copies using flash copy. And then once the background flash copy is complete, you can issue a migrate storage group command to migrate that DB2 image copy to the cloud. On this slide, we see an example of multiple enhancements coming together to provide a robust data management solution. In this environment, you can see we have storage tiering set up for the level 0 primary tier, and we have ZEDC and encryption enabled to keep the data secure and compressed to minimize the amount of space utilized. And as I mentioned earlier, you can now configure your auto migration windows to process data sets based on size. So here in this yellow box, we have an auto migration window that was set up to run for only an hour and transition data sets that were 350 megabytes in size or smaller from tier 0 to tier 1 using flash copy. So that's minimizing CPU because the data is not going through the host, and the small and medium-sized data sets, they're not migrated but kept on that least expensive online tier. And then in this yellow box on the right, we see that we could set up an auto migration window 2, and it's configured to run for 12 hours and migrate the large data sets that were not previously processed to the cloud. So you can see everything's coming together here to ensure you have adequate space, you have secure data, and you're minimizing CPU. And this next slide shows how we define a cloud to DFSMS. In order to migrate your data to the cloud, HSM needs to know which cloud the data should be directed to and how to access that cloud. And this is done using the SMS cloud construct or network connection construct. And you do that through ISMF or NaviQuest. The construct is referred to as a cloud construct on pre-2.4 systems, but on 2.4 it was renamed just to provide flexibility for future use cases. This shows the ISMF panel that is used to define a network connection to a cloud, and you enter the SMS cloud name, cloud interface type, and the identity to use when authenticating with the cloud. And here on the second page, there's space to specify a URI, port number, as well as SSL information used when communicating with the cloud. In addition to configuring automatic migration to send data to the cloud, you can also migrate to the cloud using a migrate dataset command. For the cloud parameter, you would specify the cloud name that you use when you define that cloud network connection. And HSM will invoke DSS to migrate the dataset to the cloud, and HSM will keep inventory to manage the cloud container and object prefix. This is transparent to applications and end users. There's no need to recycle. Recall works just as it does today. There is audit support for this, and volume and storage group keywords are also supported. And also consistent with traditional migration, the Valseer will be changed to Migrat. ISPF will display Migrat C for cloud, as opposed to Migrat 1 or Migrat 2. And then also consistent with traditional HSM processing, HSM will automatically recall a data set from the cloud to primary storage when it's referenced. Recall, HRecall, and ARC HRecall are all supported. The common recall queue is supported, and fast subsequent migration is supported as well. So although the last several slides emphasize TCT and cloud as the next evolution, we want to also emphasize that it's part of the journey, not the final destination. HSM and DFSMS have a history of creating new solutions to meet the changing requirements for enterprise data management, and will continue to look forward and deliver valuable enterprise solutions, and keep in mind CPU consumption and processing times as we do that. So that is the end of the presentation.
Shannon, thank you very much indeed for an absolutely excellent presentation. It covered an awful lot there, some key stuff, particularly the newer things of class transitions and slightly older but still important on-demand migration, which I think is highly usable. Does anybody have any questions? There's nothing in the chat window, so I will if anybody wants to unmute themselves and ask a question, that you should now be able to do that.
Hello. Will the presentation or a recording of the presentation be available anytime soon?
I can answer the second part. The video of the recordings will be, sorry, the video of the presentation will be made available. We're going to put them on Vimeo after the conference has ended. I'm sorry, I didn't check whether the handouts are available.
I believe I did upload them yesterday, so you should be able to see them. If you cannot, if someone could please let me know.
Yeah, I'll double check that.
Okay, thanks. It really is a lot of information.
Yes, all good stuff though. All good stuff. Any more questions? Okay, Martin has just said that he has the slides, so they're obviously there to download. Thanks, Martin.
Great.
Okay, so I'm getting the impression that that there aren't going to be any questions. So with that, thank you very much, Shannon, for an excellent presentation, for a presentation that almost exactly fits the slot, which is marvelous. So the final thing is I would like to ask people to, or ask attendees to fill in the feedback form. Shannon's put it on the screen. I've also put a link in the chat. So again, thanks very much, Shannon, and thank you everybody for attending. I'll now close the conference. Sorry, to close the session. Thanks.